Hello, and welcome to today's WJE webinar, Evaluating Chloride Contamination in Reinforced Concrete Structures. My name is Liz Pimper, and I'll be your moderator. During the next hour, materials engineer Stephen Garrett and chemist Tonya Werner will provide a brief introduction to the various standard methods available, along with a technical overview of the mechanics of chloride contamination evaluation techniques from a chemistry perspective. This presentation is copyrighted by Westjani Elster Associates. And now I will turn it over to Stephen to get us started. Stephen?
Great, thanks, Liz. So to kick us off, we'll just review the learning objectives for today. So we're going to talk through how chloride ions can become present in concrete. We'll talk through some of the sampling techniques and associated laboratory evaluation methods for determining chloride contamination in different materials. We'll explain what different chloride contamination means as far as threshold for chloride-induced corrosion in reinforced concrete structures. And then we'll close out with a brief introduction into some emerging technologies that can either complement or begin to replace some of those laboratory chemistry methods. So first of all, thanks for joining today. We had a lot of fun preparing for this webinar. Obviously, this is a topic of great interest to us. We do a lot of in-service evaluation as well as quality control checks of materials during construction. And while the test methods themselves are pretty routine, we keep learning new things on new projects, and that changes how we approach future projects and what we work into our evaluation, test, and asset management protocols. So what does chloride contamination mean to you all listening? So from a new construction standpoint, obviously suppliers, specifiers, engineers need to understand the material makeup, whether or not chlorides might be part of the contamination of these materials that are going into new structures. For those that manage existing structures, it's important to understand what chloride contaminations might exist, determining how that's going to look like going forward, and what kind of exposure conditions and future durability risk we have, and that might factor into how we plan for future asset management programs. So some of the questions we get asked quite a bit are, what are my sources of chlorides? What age and what test methods need to be utilized? And what does that mean for my structure? And today we're hoping to answer at least some of those questions. So just to go through what we're going to be talking about today, this is the outline for the presentation. We're going to all get on the same page with some of the basics of corrosion. We're going to talk through the history of how chlorides can become present in concrete from past to present. We're going to look at chloride contamination from a durability risk for our structures. We'll get into some of the chemical analysis methods for determining chloride content, talk through field sampling and data analysis to see what that means for our structures. And then, as I mentioned, talk about some emerging technologies. So to kick off, what is chloride-induced corrosion in reinforced concrete? Well, for starters, we put reinforcement in our concrete to provide tensile strength. In general, unless acted upon by other contaminants, chloride in concrete is generally protected by the alkaline or the high pH environment that's created from the cement hydration products. So all else equal, concrete structure will generally perform well until we have some sort of contamination. In general, chloride contamination, if not part of the original material contamination, can come from the outside of our structure, building up on the surface, diffusing into our structure through the cement paste, ultimately leading to corrosion action on the surface of our reinforcement. When that corrosion does occur, it's an expansive corrosion product. So essentially, iron oxide is about 7 times the volume of stable iron. And as those corrosion products build up, they result in expansive stresses that can lead to cracking, as well as the section loss of our reinforcement. Ultimately, corrosion poses not only a structural concern due to the section loss, but also aesthetic and safety concerns, both visually unappealing as well as potential spalling hazards. So chloride-induced corrosion is a pretty big problem in reinforced concrete infrastructure. So where do those chlorides come from? So there's generally 2 sources when we're looking at chloride contamination. We could call those internal or external. Internal contamination could come from admixtures or the materials themselves. Chloride-containing admixtures have been used since the 1920s to result in early strength times, particularly in cold weather conditions. But over the years, people have realized that those chlorides in the admixtures lead to corrosion. So now those admixtures themselves have been replaced with either non-chloride-containing admixtures or are still sometimes used in unreinforced flatwork applications. There's also sources of chlorides in the materials that we use, whether those are the aggregates, the mixing water, or even some of the other admixtures that are commonly used in concrete. All of those generally need to be evaluated to determine if there is a significant source of chlorides in the materials themselves. And then from an external standpoint, I think the most common source of chlorides that we think about is de-icing salts. So starting in the 1960s, chlorides have been used to increase snow melt and help maintain safe driving conditions on our highways. But since then, the amount of chlorides that have been used in de-icing practices has increased, leading to increased exposure and premature corrosion of our reinforced concrete highway infrastructure, as well as adjacent reinforced concrete structures. While we won't talk about it much during this presentation, there are other exposure conditions such as marine environments, agriculture, or industrial that all have the potential for having some sort of chloride external exposure that can affect our structures. So what does that mean? So chloride-induced corrosion of our reinforcement, as we talked about, is common and detrimental. And how do we mitigate that risk to durability of our reinforced concrete structures? Well, for starters, we can limit the amount of new chlorides that can be present in new construction. So limiting the amount of chlorides that can be present in any of our constituent materials in our new structures. We can also design our concrete appropriately, adjusting cover requirements or lowering our water cement ratio to provide more durable concrete itself. We can also use different types of steel, whether that's epoxy-coated steel, alloyed steel, which will have a higher chloride resistance than conventional uncoated rebar. And then one thing to keep in mind when we're talking about structural risk, it's not just a single static target. As structures age, there's a lot of potential for potentially changes in exposure, which could lead to more chlorides being added. Obviously, chloride contamination builds up. But there's also the concept of chloride binding. So in general, when we have chlorides in a structure, those can sometimes be bound in the cement paste as a natural process of the cement hydration. And with time, those chlorides could become free again, potentially if there's changes in environmental conditions. Typically, when carbon dioxide reacts with cement paste, those bound chlorides can be released. So it's important to understand that chloride exposure as well as internal chlorides can change with age, and that's where the engineering comes into play. So I'll briefly talk through some of these ACI limits just for reference. So we're talking about American Concrete Institute. So these are some of the design guides and codes for new structures. Now ACI 318 provides some limits for the levels of water-soluble chlorides that can be in certain concrete structures. Typically, we're looking for whether or not the concrete is pre-stressed, and then what the service conditions might be, whether those are wet or dry conditions. And ACI 318 will tell you can take a sample at between 28 to 42 days and evaluate the amount of chloride present in that concrete to comply with the code requirements. And again, that age is important because, as we know, with continued hydration of our cement, we could have some bound chlorides that get trapped in the cement paste, but could be released later in the future. One thing to keep in mind when we're looking at these chloride limits, most commonly the codes are specifying a chloride limit is a % by weight of cement. But when we're thinking about the laboratory evaluation methods, we're reporting a amount of chloride in a % by weight of sample, and typically that is the weight of concrete. So for conventional mixes, when we're looking at that 0.2% by weight of cement, that roughly correlates to about 0.03% by weight of concrete. And also important to mention that this ACI 222 document has both acid and water soluble limits. And this is a good time to pass it over to Tonya, who's going to talk through some of the laboratory methods and how we evaluate for chlorides and what that acid versus water soluble chloride concentration means.
Thanks, Stephen. So when it comes to testing for chloride in the laboratory, chloride testing is a pretty simple and basic test compared to a lot of the things we do, but there's still a lot of steps and a lot of things that we have to think through. We put together here a little bit of a history or a timeline of chloride testing in concrete, and you'll see back in the 60s, the Portland Cement Association started developing some test methods. And then in the 70s, the Federal Highway Administration joined in. And then we had ASTM methods come along. And today we have quite a few methods. And as we move into the future, we are quite certain that there are going to be a few more. So the most common places that we see chloride testing methods associated with the built world come from ASTM International and from AASHTO, or the American Association of State Highway and Transportation Officials. And just from those two places, we have quite a few test methods to choose from. And we have methods that deal with just concrete and mortar, methods that deal with raw materials from your concrete and mortar. We have water methods and even a soil method. And if that's not enough and you haven't found a method to suit your needs there's other places we can go. Many state departments of transportation have their own tweaks to some of these methods and have their own methods. The EPA has some methods. A lot of laboratories will have their own internal methods. And occasionally we'll come across some specific thing that we need to test for on a specific job, and we'll have to create our own method. The two most common ones that we deal with in the laboratory are C1152 and ASTM C1218, which are the test methods for acid and water soluble chloride. And we're going to touch on those and talk about the differences in those in just a minute. But we should note that in addition to concrete and mortar and related materials, we can also use these test methods on soil and aggregate. Water is a little different and requires a little bit different methods, but most of the methods are variations of 1152 and 1218. So almost every method that measures chloride analysis has some basic steps that are very similar. So first, we're going to need to prepare our sample that we're testing. Then we're going to need to extract the chloride out of that sample. And then we measure the chloride that came out. And while this is a very simple process, there are things that make each step a little more complicated. So we have to think through before we can prepare our sample, what type of sample do we have and what condition is it in? When we're going to do an extraction, we have to think about the type of chloride that we're looking for, that we want to extract out of that sample. And when we get ready to measure the chloride, we have to think about our measurement method and what goes into that particular method that we're using. So we already talked a little bit about types of samples, but mostly we're dealing with concrete, mortar, grout, those types of cementitious materials. But we sometimes need to look at the raw materials that go into the concrete, especially with newer construction. So we might need to look at cement or aggregate, water, maybe even your admixtures. But chloride can get into your concrete from external sources as well. So there's times where we have to look at things like soil or maybe water that the concrete is exposed to. And in some situations, we might even look at corrosion product itself when we're trying to figure out what's going on in a particular project. So based on your sample and the condition that your sample is in, there are some ways that we might have to prep that sample before we can use it in the lab. So with concrete, we're probably going to have to do some slicing. We often have to do grinding to grind it into a powder. If you're grinding a lot of a sample, you're going to need to split it to make sure that you get a representative sample in the end. And occasionally there's some unique preparation techniques that have to be done to be able to look at a specific area or to understand a specific problem. There are also interferences that we see in the laboratory. There's things like sulfide and iron that can interfere with your measurement procedure. And we want to look for those types of things at this sample prep step, because if we can remove those during this step, it's a whole lot easier to deal with in the laboratory. So ASTM C1152 and 1218 does give us a little bit of a guideline when it comes to how to take samples. Those guidelines tell us that if we take a concrete core and the diameter meets ASTM C42 requirements, we can take a 1/2-inch longitudinal slice down the center of that core, and it should be representative of the core itself. We can also take 1/2-inch lateral slices to use for profiles. So if we want to know if the chloride at the top of the core is the same as the chloride at the bottom of the core, a 1/2-inch slice will work for that. Those sampling guidelines also tell us that for mortars, the aggregate is smaller, so we can take a smaller sample size. So what is about C42? What are the requirements we need to think about? And 2 of them are that we need to be at least 3.7 inches in diameter for our concrete core, and that the diameter of the core should be 2 times the nominal size of the aggregate. So you see the common denominator here has to do with the aggregate size. And why is that? So what you want to think about is your paste to aggregate ratio. And I really like this sample because there's a very big contrast between the aggregate and the paste. So if you look, you can see that there's the very dark aggregate and the lighter paste. And if we were to take a sample from 1.5 to 2 inches and cut that slice, the part that we can see at least has about 75% paste and 25% aggregate. If you skip down and take a slice around 2 to 2.5 inches, you see that it's kind of the opposite. In that slice, the aggregate is now 75% and the paste is only 25%. And the reason that matters is because when chloride infiltrates into your concrete, it's going to travel through your paste, not through your aggregate. So you want to pay attention to your paste to aggregate ratio and make sure that the sample you're taking is representative of the area that you want to measure, so that the differences in your chloride concentration are actually due to chloride concentration and not differences just in your sample makeup. And so this will mean that there are times where you might need to take bigger than a 1/2-inch slice, and there are times where you might want to take a smaller slice, and that would be appropriate if your paste to aggregate ratio allows. So once we get our sample prepped, now we need to extract the chlorine ion out of it. And the first thing we need to think about is our extraction medium. And we've been talking about the difference between water and acid-soluble chloride. And we're going to cover that in just a minute in a little more detail. But basically, you want to decide if you want to use water or acid to pull the chloride out of your sample. And then you need to think about how you're going to do that. So you may need to stir your sample, you may need to heat it, there may be cycling where your water or acid is pouring over your sample. And when you get all your chloride out, you want to filter out your non-soluble parts and just look at the soluble portion of your sample. So when you're deciding if you're going to use acid or water, we want to think about the types of chloride that we're looking at. So if you think of all the chloride in your sample as your total chloride, the part that dissolves in acid is acid soluble. And that acid soluble portion, when it comes to concrete and mortar, is typically very close or the same as your total. So that acid is going to break things down and pull out the majority of your chloride. Then with water soluble, only the portions of chloride that are soluble in water are going to come out. And we call this the free chloride. And the free chloride, or the water soluble, is the chloride in your sample that is currently available. It's currently free and around and able to cause corrosion. That portion that was acid soluble but not water soluble, we call that bound chloride. And at this moment in time, that bound chloride is not currently available. But as Stephen talks about, these things can change over time. There can be forces from your environment. There can be things that have to do with hydration that can make your chloride types change from bound to unbound or from water to acid soluble. So when you're choosing your extraction procedure, you want to think through what you're looking for and why you're looking for it and choose an appropriate method. And then it comes time to measure the amount of chloride we extracted out. And there's lots of ways to do this. A couple of ends of the spectrum. One side is strips or tubes. So you can actually get chloride strips or chloride tubes. And I think of these as kind of like pH paper. This is an example of a Kitagawa tube. And you can see at the top where the yellow arrow is, when the solution comes up through the tube, when it reaches the top, it turns yellow and you know your test is done. And if you look near the red arrow, you can see the indicator changed around 100 ppm. So that tells us that there's around 100 ppm of chloride in that sample. So these types of strips or tubes can be nice when you're maybe out in the field or someplace where you cannot use a full accurate analysis of chloride, but you want to have a general idea if there's a lot or a little. On the other end of the spectrum, we have things like ion chromatography. Ion chromatography can be very accurate, and it's often used with water samples because there's very little sample prep involved, or you can use it after you've extracted your water-soluble chloride. The method that is most generally used and that we use here in our laboratory is called potentiometric titration. And basically for potentiometric titration, we just take our extracted chloride, we put electrodes into the solution, and we record the millivolt readings or the potential between those electrodes. We then add known amounts of silver nitrate, and this will react with the chloride and form a precipitate. That precipitate will change your millivolt readings, and you keep adding until you get to your endpoint. So you record all your values, and your endpoint is something that we can mathematically calculate, and that is the point where all your chloride is consumed. And this can be done automatically or with an automatic titrator or manually, but it can be extremely accurate. So now I'm going to send this back to Stephen, who's going to talk to us a little bit about what to do with this data.
Great, thanks, Tonya. So now that we have a great sense on how chlorides can get into concrete and how we evaluate them, we're going to talk through field sampling techniques and then evaluation of corrosion risk in our reinforced concrete infrastructure. So to get samples from the field, in general, if we're talking about new construction and we're sampling of the constituents, we can generally sample those on site, whether that's the mixing water or the aggregate stockpiles. When we're looking at existing structures that are exposed to exposed to chlorides, most generally we want to take core samples. For many of the reasons Tonya talked about, we want to get a large enough sample to be able to overcome any aggregate effects when we're evaluating chloride in any slices. We'll generally need to take samples across the structure in different exposure zones to truly understand differences in concrete placement as well as differences in surface buildup from chloride exposure. In some cases, we're not always able to take a core sample, whether we're limited by access or limited by restrictions of the structure. We can take powder samples through drilling into the concrete and collecting the resulting powder, whether in a bag or in a vacuum. In general, we wouldn't use powder samples for an in-depth analysis just because of the limitations. Can be used as a screening method to see, the approximate or rough levels of chlorides. The reason powder samples aren't ideal is we have just a small location that we're drilling into. There's some variability in the depth of how we're getting the sample extracted. And then if there's large aggregates, as Tonya mentioned, those might impact the powder that we're collecting if it's, hitting an aggregate versus hitting the paste. Generally, we have a little bit of a challenge interpreting the results. For other structures, the exposure, we can sample the water or the soils to see what's going on the outside of the structure and then compare that to the exposure we're seeing within. When we're talking about water samples, sometimes we're looking at pools or groundwater sources or industrial applications, and I'll get into one of those in one of the case studies here in a little bit. And we can also sample the soils, whether that's native or backfill, because both could be contaminated and could be a source of exposure. But looking at chloride slices for chloride concentration profiles, this is how we might lay out testing in a core sample. So what we have here is a core sample that we've illustratively marked out with the depths of the slices that we're going to collect. And this is pretty typical for how we would approach an assessment project. So what we're showing here is a couple slices through the surface. So this will show us the chloride contamination in the upper portion of the concrete, both at the surface for the exposure source, as well as how much chloride is diffusing into the structure. We'll generally also take a depth directly over the reinforcement, calling it a cover depth slice. So this will tell us at the time of the assessment what were the chloride levels right above the rebar, and how will that factor into the corrosion risk. And another thing we'll generally do for existing structures is take what we would call a background slice. So this would be a slice deeper in the core sample, away from any external exposure. And this will hopefully tell us if there is any internal exposure present from original construction. And for that background slice, generally we'll test both acid and water soluble to see if the aggregate component is a primary factor. So if we test for acid soluble and it's higher than the water soluble, that might mean indicate bound chlorides or chlorides in the aggregates that could affect our results. One thing to note, typically when we're doing these surface slices, we're going a little thinner, a quarter inch to an eighth inch if the aggregate size allows us. And this helps us get a detailed chloride profile, ingress profile into our core sample. So illustratively, we'll typically present chloride concentration plot. So this plot is showing on the x-axis the depth from the surface, and on the y-axis we're plotting the chloride concentration as a percent by weight of concrete. So this is the percent by weight of the sample. So you can see through the surface how we're getting our chloride ingress into our structure, and then both our cover depth and background slice. In this case, we're below what we're calling the corrosion threshold, and that's that 0.03% by weight of concrete. And I'll get into a little bit more about what that threshold looks like in a little bit. But essentially, this is the common way we're going to be presenting and interpreting our chloride concentration profiles. Another important consideration when we're evaluating structures is the presence of cracking. So in general, cracking is an inevitability in our concrete structures, and we need to evaluate how those cracks might be letting chlorides into our structure, and to what magnitude and extent this is a problem. Just some examples of cores with cracks through them. We can see how a crack will generally extend down to the reinforcement until that reinforcement takes over and kind of tightens up the crack. So generally cracks will be larger at the surface and taper down, but still they provide a direct path to the rebar or to the deeper portions of the concrete for chlorides to ingress to. And this is a great example showing two chloride profiles adjacent to each other. One being an uncracked core, so that's the blue line, our blue chloride profile showing decreasing chloride concentrations with depth. And then the orange line is showing a chloride profile at a crack. So what we're seeing is a much more elevated level of chloride contamination through that concrete, certainly even deeper into the substrate beyond 2 and 4 inches there relative to the uncracked. So certainly cracking poses a significant risk and should be addressed separately when we're doing our assessments. So I was mentioning the idea of this chloride threshold for corrosion. Oftentimes it's thought of as a single value, but more realistically, it's a probability distribution. So what we're looking at here is changes in chloride content on the x-axis, and then the probability of corrosion initiation on the right. So remember that 0.2% by weight cement or 0.03% by weight concrete that's commonly used as a limit for new construction. And that's a conservative limit because essentially below that limit, there should be negligible corrosion. But it doesn't mean that for a structure and service, if you exceed that limit due to exposure, that you're going to immediately have corrosion. So this is where looking at probability of corrosion based on chloride content is important. Essentially, as you get higher chloride concentrations, probability of corrosions increases accordingly. And this is different for different reinforcement materials. So as I'm getting into some of these case studies, we can look at the case of uncoated rebar versus epoxy coated rebar and how that might differ. So going through some case studies here on reinforced concrete infrastructure, we often get tasked with performing corrosion risk assessments or asset management programs to determine, what's the risk for durability, what can be done to protect the structure going forward, and what kind of repairs are appropriate given the exposure and construction conditions. And certainly chloride concentration testing plays a huge role in assessment of reinforced concrete infrastructure. One project that we've done over the years was assessing a series of bridge decks that had epoxy-coated rebar. The goal of this assessment was to determine how that epoxy-coated rebar was performing for these structures that were built in, I believe, the 70s, and what was the future going to look like for rehabilitation needs and end of service life. So to evaluate the epoxy-coated rebar, we wound up collecting core samples through portions of the bar where we were able to extract the bar sample on portions with enough reinforcement and non-critical structural zones to sample one of the bars. We then did chloride profiles through those cores, not only to evaluate the exposure, but also specifically to see what the chloride concentration was right above that epoxy-coated rebar, and then taking those samples back to assessing the corrosion condition of that rebar itself, with the hopes of developing a comparable chloride probability distribution for corrosion risk in those epoxy bars. So here's some from that study, and it is one of the attachments, references in this webinar. Essentially, we were able to observe a range in the conditions of those epoxy bars, from essentially no evidence of corrosion to areas of widespread active corrosion, and then compared that corrosion condition to the chloride concentrations that were present above those bars. That helped us look at or develop a corrosion risk distribution for epoxy-coated rebar. Now, getting into too much of the statistics, the takeaway here is that for uncoated rebar, we're looking at that chloride threshold. The average was about 0.5 by weight of cement, and then looking at epoxy bars, and the average threshold for chloride-induced corrosion was about double of uncoated rebar, owing to the ability of the epoxy to somewhat resist chlorides and provide better performance. So this became important as far as developing asset management plans and corrosion projection risks for these bridges. Another item that's come up in our work is how do these bridges perform long-term, both exposure as well as performance of these bridges over time in service. So in 2023, we went back to a series of structures that we had pretty detailed chloride data on, and wound up collecting additional core samples and evaluating both changes in as well as changes in the chloride diffusion characteristics. So about 12 years apart, what we're seeing in these plots are some examples of chloride concentration profiles. The blue curves being the 2011 data, and the orange curves being the 2023 data, all for uncracked core samples over these series of bridges. In general, we saw the expected behavior of similar surface concentrations, but with additional chloride buildup or chloride ingress with age. Now, one thing we did notice in a few locations, what we called unexpected behavior or somewhat apparent changes in surface concentration. So that's this figure on the right here, where there was apparently some increase in the surface concentration, even though we were taking core samples pretty close together. Ultimately, we decided to look into this further and concluded that, in general, chloride surface concentration could be quite variable. So looking at the full data set from this study, we had about 7 bridges that were included. We had 40 uncracked core samples. And then this histogram we're showing is the chloride surface concentration we measured from our laboratory testing. While on average we were at about 0.4% by weight of concrete, that surface concentration value ranged from 0.1 to 1% by weight of concrete. So pretty wide distribution in surface exposure. Thinking about this, we could say that there's probably some variability across the structure, even though they're all being exposed to de-icing agents. There's material variability. There's variability in rain events. There's variability in where snow and salt might build up in certain areas due to drainage. So ultimately, the takeaway from this was that when we're going out to do an assessment, we need to make sure we're evaluating exposure appropriately and taking a sufficient number of samples to characterize both the exposure and the diffusion into our concrete structures. Switching gears a little bit, we have performed some cooling tower assessments over the years. For those that aren't aware, in power generation, essentially there's a turbine, a steam turbine that creates electricity through whatever means, and then that water needs to be cooled In the case of a natural draft cooling tower, it's pumped through the top, filtered through a series of traps and vents, and then that steam evaporates, water cools, and it's pushed back into the process to be repeated and used for more power generation. We had looked at a tower that was known to be sourcing their water from a brackish body of water, so slightly salt water. And then, as you can imagine, as that water continues to get processed through the plant, that salt concentration could build up as the fresh water evaporates. So prior to doing any concrete work, we took a sample from one of the towers in service, did a laboratory evaluation, and found that the chloride levels were elevated. And in this case, above drinking water, and certainly enough to pose a risk for chloride exposure and deposition onto our reinforced concrete structure. So then, as part of our broader assessment, we looked at all the different columns and reinforced concrete elements, first to characterize our corrosion conditions, but then to select locations for material samples. This is an interesting plot because we can see how collecting two core samples from the same column, both at the top and the bottom, we're seeing widely different chloride ingress profiles. In both of these cases, the cores were uncracked, but just being at the top of the concrete where there may be more exposure to that steam or the water dripping down, there's a significant more chloride buildup that we observed. Now, the other thing we noticed in that core from the top is that the immediate surface chloride was lower than the chloride levels just a little bit deeper into the concrete. This could be attributed to differences in washing behavior, wetting and drying cycles, but ultimately the takeaway is that it is important to do those several near surface slices in order to get an accurate assessment of the chloride profile and the chloride ingress into your structure. Ultimately, as part of all of this, we're taking this data and we're doing asset management. And chloride testing is a small part of that, but it's important to understand the chloride diffusion behavior as well as the construction in order to do appropriate service life modeling and asset management. Essentially, with service life modeling, is we're looking to project damage into the future and then evaluate, when our structure might reach its end of life, and then further to evaluate extension strategies, whether that's coatings or sealers to limit future chloride ingress, concrete repairs to address damaged areas, or even corrosion protection methods like galvanic or impressed current cathodic protection. So ultimately, chloride testing is a small portion of a much broader area of practice within forensic engineering. And then with that, I'm going to turn it back to Tonya, who's going to talk through some the emerging technologies we're seeing in this space.
Thanks, Stephen. So in the laboratory, we are constantly looking for ways that we can get more and better data and information with our testing labs. And when it comes to chloride analysis, one of the things that we have been looking into has been techniques. So elemental mapping techniques basically are able to measure the elemental concentration on the surface of a material. So it can directly measure the surface of your concrete. And that measurement area is really very small, but you take a lot of measurements and add them all together so that you're basically mapping out your sample. When you get your data, that data can be color-coded based on your element and also the concentration of that element. So what you end up with is almost basically a picture of exactly where those elemental concentrations are on your sample. And two examples of this type of mapping technique include LIBS, which is laser-induced breakdown spectroscopy, and also micro XRF or micro X-ray fluorescence. So for elemental mapping techniques, these would be very good for us to use in chloride testing because they require first minimal sample preparation. We can just cut open a concrete core and we can look at that surface. We don't have to do the slicing and the grinding and those types of things. You also get more data points than you do for traditional testing. So if you think about with the traditional testing, when we have to take that slice and we get one data point for an entire slice, with the mapping techniques, we can take several several measurements in the same amount of area that we could just get one measurement from before. So this helps a lot, especially at, say, the surface of your core where you're trying to get more data points. You also can get a more detailed analysis of a very small area. So when you're looking at something like a crack, we can see how that chloride is diffusing through the crack by using these mapping techniques. And for all the chemists out there, it's very nice because there's no titrating involved. So in order to explore these methods, we decided to do a bit of a laboratory case study. So we batched some concrete samples, and half of those samples used a chloride-containing aggregate, and half of them did not. And then we added chloride to the paste in some of these samples and not in others. We then took representative cores of all of this concrete, and we tested them by our typical wet chemical methods. And we also sent them out to be tested with mapping techniques. And in this case, we started out with LIBS testing. So we sent this out and we were able to get results from 2 different laboratories for the LIBS testing. And the data from each lab was reported with and without aggregate. So they were able to use software to remove the aggregate, and we could calculate separately the chloride that was in the aggregate and the chloride that was in the paste. The images we received showed relative concentrations of chloride. And then each lab, though, reported their data in different units. And Stephen talked about the importance of understanding the difference between the chloride by weight of sample and the chloride by weight of paste or by cement or cementitious materials. And each lab reported these things differently. So it took a little bit of math to be able to compare these samples together. And we don't have enough time today to go into all the details, but there were a few takeaways from this that we wanted to highlight. What this test did was kind of highlight for us exactly the areas that we should be looking at when we're evaluating these newer technologies. So when it comes to sample type, we want to pay attention to the fact that these new emerging mapping techniques are taking samples that are non-uniform, and they are also looking and doing this testing in situ, which means in place. So basically the concrete, one spot might be an aggregate, the next spot might be a paste sample. So that's very, very different from the testing we've done before, where we grind up our sample and try to make it as uniform as possible and then extract the chloride out. And so again, we're not going to go a lot into details, but just know that these are very different things in the laboratory when it comes to measurement. The other thing we want to think about is with our chloride type. We talk about total and acid and water-soluble chloride. These emerging technologies are measuring the total chloride. They're looking at everything that's available in the sample. Up until now, most of our testing has been done with acid and water-soluble chloride. So this is good. We want to be able to see the difference between the paste and the aggregate, but we need to think about how we're going to use that information and use that data, because the majority of the guidelines and specifications in place are all based on acid and water. So we need to think those through when we're using our chloride data. And lastly, we have to think through these measurement methods. So when you're using these instruments, some of the things that we need to think about are things like detection limit and calibration. Stephen was talking about the threshold limits and knowing that our threshold is at about 0.2% by weight of cement. We need to make sure that we're using instruments that can actually see chloride at 0.2% by weight of cement or 0.03 by weight of concrete. We also need to think through how we're going to calibrate these instruments with non-uniform samples. We need to make sure that we have knowns or calibration standards that are going to work well. And we also have to think about things like precision and accuracy. Precision means that if I run the test 10 times, do I get the same answer all 10 times? And then accuracy is how close is that data to the actual data. And this is only a concern because in the past, we've had lots of time to deal with the acid and the water soluble methods and techniques. We've done interlab studies and things, and we know how accurate and precise a lot of those methods are. And we just don't have that information yet for these newer technologies. So these are all things that we want to keep our eye on when it comes to not only these techniques, but any that might be coming forward in the future. So we want to make sure we leave some time for questions, but we also know that we threw a lot of information at you in a little less than an hour. So we want to give you a little bit of a summary here of some of the key points and key takeaways. We want you to remember that chlorides will affect your corrosion resistance of your reinforcement, that they can cause that corrosion. And there are many, many sources of chlorides that will affect the built world. They're not just in chloride-containing admixtures. They can be internal and external sources. We need to think about field sampling and make sure that you are taking samples that will actually help you meet your goals. Make sure you have enough samples and they're taken from the right places. And once you get your samples, please coordinate with your testing agency. Make sure that your testing lab knows what your needs are so that they're using the proper test methods and getting you the data that's actually going to help you achieve your goals. It's also important to know that every structure is unique in both its construction and its exposure. And you need to understand all those things so that you can correctly and appropriately identify what your corrosion risk is. It's not a one-size-fits-all. And lastly, chloride testing is a very dynamic field. It's constantly changing. There are a lot of methods. There will be a lot of methods in the future. And you want to make sure that you are talking with your lab and staying on top of what's happening with those test methods. So with that, we would like to thank you very much for your time and for sharing your time with us today. And I'm going to give it back to Liz for the Q&A.
All right. Thank you, Tonya, and thank you, Stephen. We are going to turn now to questions. Okay, our first question. Around what time frame did the practice of eliminating chloride-containing concrete admixtures begin?
Ooh.
Yeah, I believe it was up in those ACI limits came about in the 1970s. So up through that time, they were still using it even in reinforced concrete, even though the risk for corrosion was known. Now, it's important to note that those chloride-containing admixtures are still used. They're still manufactured and used most commonly in, flat work like sidewalks and driveways and non-reinforced applications for winter construction. But it can get mixed up if it's not treated properly in the production facility, which is all the more reason to do the testing.
Okay, our next question. For a 0.03% chloride limit by weight of concrete, is that current with the type 1L and SCM replacements?
Yep, so that, those limits are, the ACI limits generally, they've been updated to percent by weight of cementitious material. So it is considering all sorts of cementitious. I think the bigger question there is, do type 1L cements provide the same protection as Portland cement as far as the chloride threshold? And I believe currently there's some work being done within ACI to evaluate those corrosion thresholds. I don't know if type 1L cements are specifically listed in those current ACI 318 limits, but I know other supplementary cementitious materials are. Tonya, do you have anything to add on that?
Not really, just that you need to be sure that you are chatting with your testing lab and make sure that you're understanding how they're reporting and what they're including in their calculations.
Okay, our next question. Is the background chloride slice also beneficial for carbonation testing at the soffit?
Yeah, that's a good question. It depends on how far the core went down. I mean, when we're talking about a background slice, it's from the middle point of the structure away from either topside or underside exposure. In general, we would do carbonation testing on any core sample or even in the field, whether that's the surface or the soffit. I think that's often part of a petrographic examination or other laboratory work that's performed in conjunction with chloride testing. And we would probably just do a pH indicator on the full core sample itself rather than on a slice.
Okay. Have you used electronic testing such as the profometer or profometer with a wet electrode or a rolling wet electrode to develop a heat map, so to speak, of high areas of corrosion and low areas?
Yeah, that's a good question. So that sounds like related to more of the broader field investigations that generally go into reinforced concrete assessment. Oftentimes in addition to visual work, we're doing corrosion testing like half cell potential or resistivity, and doing those methods in advance will help us, first of all, locate the material samples, but also provide broader context to whatever we're going to measure from our lab samples. So if we're finding areas of high and low corrosion activity in our potential, maps, we'll take a core from both and then try to correlate chloride concentrations relative to, the corrosion measurements that we're seeing.
Okay. Why would a large bridge pier in a marine environment have a different level of chloride ion concentration on different sides, as in north versus south or east versus west?
Yeah, sure. I mean, without having more information about location and exposure, it's hard to tell. But in general, when we're talking about marine structures, it's more about the zone relative to high tide. So there's what we would call submerged zone below water. There's a tidal zone right near the tidal line, and then the splash and atmospheric zone. In general, if you have a side that maybe gets more rainwater than others, you might have some surface washing off the structure. So the chlorides on the surface might wash off, and then there'll be less to diffuse into the structure. If you have a side that's exposed to, wind-driven chlorides or higher splash activity, and then you get marine water splashing on your structure and wetting and drying, that's going to accelerate the buildup on the surface, and then that's going to push concrete through the diffusion process.
Okay. I believe this is a question for Tonya. Is there an ASTM or AASHTO test method for the chloride measurement using potentiometric titration, or was this method developed by the WJE laboratory?
The majority of ASTM test methods actually reference potentiometric titration, and it is the method I believe is most commonly used.
Okay. Next question. What if the rebar spacing is tight and the core cannot be extracted?
Yeah, I mean, it depends on the goals. If you can reduce your core size, ideally we want to get a 4-inch diameter core and take slices that are generally compliant with the standard. Aggregate size is going to affect, our laboratory test results, so we need to keep that in mind. If you cannot get a core at all, you may be able to do powder sampling. So this is where we'll, as I mentioned, we'll drill into the structure at incremental depths, collect the sample, maybe from 0 to a half inch to 1 inch, or what have you. But those are really only for screening and evaluating if you have chlorides at all, just because there's so much error and noise that'll be in the data, just from variability in depth. You don't really know how many aggregates you're hitting at your drill points. So generally, the sample if possible, and then only when you cannot get a core sample at all would you shift to the powder sampling.
Okay. Is there a correlation between the current ASTM of chloride testing and the new emerging technologies like LIBS?
I have not seen one yet. Theoretically, there should be. We are still looking into that testing and trying to understand a little bit better the things like the plus and minus range, the detection limit, those types of things. So maybe we'll see.
Okay. Is ACI or ASTM developing testing methods for these emerging chloride testing technologies?
Not that I know of at this time. I guess I'll just leave it at that.
Okay. Are carbonation states usually tested concurrently with chloride ion assessments?
Yes, I mean, in general, if we're doing a, broader corrosion risk assessment on a structure, we'll perform carbonation testing. We can do that through drilling through the structure at incremental depths and applying a pH indicator in the field, or when we take core samples back to the laboratory, we can apply different pH indicators to evaluate the change in pH, and that'll be correlated to that carbonation front through the structure.
Okay. I think we have time for about one more question. Do you suggest preventative measures for existing structures, and what design and engineering strategies can be introduced to mitigate chloride contamination?
Sure. Yeah. I mean, there's a lot to those questions. It's obviously a big field of practice, right? So when we're talking about durable design for new structures, we're thinking about all aspects of future exposure. We're thinking about developing mix designs that are appropriate to resist chloride diffusion in service. I mentioned briefly service life modeling. There's a lot of work being done for developing service life models to meet 50, 75, 100-year targets of service life for any new design. And then obviously it comes down to providing the right concrete mixtures, detailing cover it appropriately, specifying the right reinforcement, and then building it correctly. Now, if you're talking about a structure that's been in service and now is being exposed to chlorides and potentially showing signs of deterioration, the goal of these asset management programs and investigations is to determine, what the root cause of that deterioration is, quantify the exposure, and then, think about, is it okay to just do sealing activities to prevent additional chlorides from getting in? Do we need to, potentially mill or remove the surface of a structure and do a new overlay, which doesn't have chlorides in it, and we've removed that portion of the chloride contaminated concrete? Or do we need to get into advanced corrosion protection measures on our structures, like galvanic anodes and press current systems? And then, beyond that, there's advanced methods of realkalization or electrochemical chloride extraction that get more and more expensive, but can be used on the right projects. For example, a lot of historic preservation and unique construction utilizes those methods, and the cost is justified relative to the service life extension. So, yeah, there's a lot to that topic, but certainly plenty of options available.
Okay. Well, thank you, Stephen, and thank you, Tonya, again for the great presentation. And thank you all for joining us. We hope it's been educational. So finally, Stephen, Tonya, anything else you'd like to leave with the audience today?
No, thanks for joining today. Great discussions, great questions, and reach out anytime.
Okay, fantastic. Thank you so much for your time, and we hope you have a great rest of the day.